All right, folks, here in section 5.4, we're going to utilize the second derivative test and optimization. We've already seen in one section optimization, and that took place on a closed interval. So in section 5.4, we're going to look at optimization on intervals that are not closed. The objectives we're going to look at in section 5.4. Objective 1 is use the second derivative test to determine relative extrema. This is really just going to get us used to the second derivative test. Then we're going to use the second derivative test to apply or to determine absolute minimum. This is where the power of the second derivative test and optimization is going to come into play. Objective 3, we'll look at an example where we apply it to maximizing a volume. And then objective 4, we're going to look at it at the second derivative test and apply it to maximize a harvest. So the second derivative test, without further ado, let's just jump right into it. For a function that has a second derivative, the second derivative exists on an open interval containing c. And it has a critical value x equals c, where f prime of c equals 0. The point c f of c is a, and now before I go any further, I want to point out in the second derivative test, it's focusing on a critical value where the derivative is 0. Remember, in general, critical values occur wherever the derivative is 0 or where the derivative is undefined. We're only going to be concerned with critical values where the derivative is 0 in the second derivative test. So the point c f of c, well, number one, it's a relative minimum if the second derivative evaluated at c, well, if it's greater than 0. It's a relative maximum if the second derivative evaluated at c is less than 0. So c is a critical value where the derivative is 0. If the second derivative evaluated at c is positive, then you have a relative min at x equals c. If the second derivative evaluated at c is negative, well, then you have a relative max at x equals c. And, pictorially, this should kind of make some sense. I mean, look at the point there, c f of c. It is a critical value. C is a critical value because the derivative is 0. If you draw a tangent line there at c f of c, it's a horizontal tangent line. So the derivative is 0. The second derivative evaluated at c would be positive because look at the graph. It's concave up. Likewise, for a relative max, second derivative negative, you'd be concave down. And then a quick note, the second derivative test that fails if f double prime of c is equal to 0, or it's undefined. I say in this case, the first derivative test may be used. Okay, now before I go any further, I would say if all I'm asked to do is to determine relative max or relative min, I'm going to use the first derivative test. It's short, it's sweet, we know how to use it. The second derivative test has its importance in looking at applications where the interval is not closed. So with that said, I would like to just practice the mechanics of the second derivative test in this example. We'll use the second derivative test to locate the relative extrema for that function. So you know the drill. Write this example into your notes because I'm heading off to the chalkboard to work through it. All right, folks, this example, we're asked to use the second derivative test to locate the relative extrema for this function. So this example is just, we're just trying to get down the mechanics of what the second derivative test says. So first things first, we need to find critical numbers or critical values where the derivative is 0. That's it. That's the only thing that the second derivative test pertains to, are the critical values where the derivative is 0. So I better get the derivative. And the derivative is 12x squared plus a 14x minus 6. Let's determine where that's equal to 0. And I'm going to go ahead and factor out a 2. And now I have to try to factor, hopefully factor, that trinomial. And it factors to 3x minus 1 times 2x plus 3. So the critical values where the derivative is equal to 0, set each of these factors equal to 0, you get 1/3 and -3/2. All right, so now we're going to apply the second derivative test, which means we have to get the second derivative. So let me come over here and write down the second derivative. See, the second derivative is 24x plus 14. All right, so now I evaluate the second derivative at each of these critical values. So let me start off by evaluating the second derivative at 1/3. So if I evaluate the second derivative at 1/3, so I put 1/3 in for the x, I end up getting 22. Well, 22 is definitely a positive number. So that tells us we have a relative minimum at x equals 1/3. Specifically, it's at the point 1/3, and then I have to put 1/3 back into the function, and when I do that, I get, as a fraction, I get 187 over 27. I believe as a decimal, this would be 6.925, where the 925 repeats. Okay, next, the other critical value where the derivative was 0, -3/2. So I evaluate the second derivative at -3/2. So I put -3/2 in to the second derivative, and I think I get -22, which is definitely a negative number. It's less than 0. So that tells us we have a relative max at -3/2. And specifically, it's at the point -3/2. And again, I put -3/2 back into the original function. The y value is 77 over 4. So that's the mechanics of the second derivative test. So let's head back to the slides so we can start to talk about what we're really going to use the second derivative test for, and that's finding absolute extrema. All right, folks, now that we've seen the mechanics of the second derivative test, let me mention one more time. In a previous section, we found the absolute extrema, the absolute maxes and absolute mins. We did that on a closed interval because remember, a closed interval guaranteed the function had both an absolute maximum and an absolute minimum. If we have an open interval, well, there is no guarantee that there's an absolute max or an absolute minimum. So let's reformulate our second derivative test, but now let's look at it for just the absolute extrema case. So if you have a continuous function f on any interval, open, closed, or half open, and if x equals c is the only critical value in the interval where f prime of c is 0, well, if the second derivative exists, then the point cf of c is an absolute minimum if the second derivative evaluated at c is positive. It's an absolute maximum if the second derivative evaluated at c is negative. And then if second derivative is 0, well, we don't know what's going on. The second derivative test for absolute extrema, it fails. So let's look at a quick example to now practice the mechanics of using the second derivative test to find an absolute minimum. So, write this example in your notes. because we're going to look at finding the absolute minimum for that function on the open interval 0 to infinity. So get in your notes because I'm heading off to the chalkboard. All right, folks, here we're going to use the second derivative test to determine the absolute minimum for this function on the interval 0 to infinity. So I have to start off by getting the derivative. So the derivative, let's see, the quotient rule. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, which is 1, all over the denominator squared. And if I just clean this up a little, it's an 8x squared minus 4x squared minus 20, or 4x squared minus 20 over x squared. So keep in mind, we want to know where the derivative equals 0, so we can use the power of the second derivative test for absolute extrema. So my derivative kind of looks like a fraction. Remember, the only time a fraction is going to equal 0 is when the numerator equals 0. So I take the numerator, set it equal to 0, and I add 20 to both sides, divide both sides by 4. I get x squared equals 5. So x equals plus or minus the square root 5. So on the interval 0 to infinity, we don't care about the negative square root 5. That's not on the interval. So on the interval 0 to infinity, we're only interested in the square root of 5. All right, so now to apply the power of the second derivative test, I need to compute the second derivative. So let me come over here to do that. Second derivative, all right, so here's my first derivative. I'm going to crank it through the quotient rule. So that would give me derivative of the numerator, 8x, times the denominator, minus the numerator times the derivative of the denominator, which is 2x, all over the denominator squared. So x squared squared is x to the 4th. You know, I'm going to clean this up just a little bit because it doesn't take much to say that's an 8x cubed. And then I'll distribute a negative 2x here to get a negative 8x cubed plus a 40x. And notice that that immediately simplifies down to a 40x over x to the 4th. Or, how about that? 40 over x cubed. So now when I evaluate the second derivative at the critical number, at the critical value, x equals square root 5. So when I evaluate it, I don't even need to use a calculator. I know square root 5, when it comes in here, I know square root 5 cubed is positive. Positive divided by a positive is positive. I know it's going to be greater than 0, which tells me we have an absolute minimum at x equals square root 5. Or, let me write that as an ordered pair. Square root 5, that's the x value, and I put square root 5 back into the original function for x, and I'm just going to list the decimal here. I get it to be about 17.89. All right, so you know what? I'd like you to practice one of these. So in section 5.4 exercises, go ahead and try number 31. So pause the video, do number 31, restart the video. I'll be here at the board working through it. All right, number 31, you were asked to get the absolute maximum for the function f of x equals negative 2x minus 9 over x on the open interval 0 to 20. I went ahead and did my first step of rewriting the function. I'd rather see 9 over x written as 9x to the negative first, because that way I could quickly compute the derivative to be a negative 2 plus 9x to the negative second. And I'm going to come over here and also write down what the second derivative is. So the second derivative is a negative 18x to the negative third. Alright, so here's our derivative. We want to know where the derivative is equal to 0. So we take the derivative, set it equal to 0. And I'm going to go ahead and do a step of algebra as I set it equal to 0. And that's rewriting this negative exponent as 9 over x squared. Then I'd add 2 to both sides. Multiply both sides by x squared. Divide both sides by 2. Take the square root of both sides and I get plus or minus the square root of 9 halves. Well, the square root of 9 is 3. So plus or minus 3 over the square root 2. So there are two values of x, two critical values, where the derivative is 0. But on the interval 0 to 20, there's only one. And that's the positive square root 3 over 2. So we only care about the positive 3 over the square root 2. So now I evaluate the second derivative. Oops. And, you know, I'm going to clean up the second derivative a little bit. I have enough room here to simplify it. You know, keep in mind that would simplify to negative 18 over x cubed. So I have negative 18 over 3 over the square root 2 quantity cubed. I don't need a calculator for this at all. I know 3 over square root 2 cubed is a positive number. Negative 18 divided by a positive number. Well, negative 18 divided by a positive, negative divided by a positive is negative. Since it's negative, that tells us we have an absolute maximum at this value of x, 3 over square root 2. I'll write it as an ordered pair. 3 over square root 2 comma. Okay, now I have to take 3 over square root 2 and toss it back into the original function for x. And I used my calculator and I got the decimal approximation of negative 8.49. In fact, if you had the decimal approximation for 3 over square root 2, I'd be okay with that because that's a 2.12. So I'd be okay with that as telling me what the absolute max is. Alright, that's the mechanics of the second derivative test. Its usefulness is finding absolute extrema on an open interval. So I bet when we go back to the slides, we're going to start looking at applications. All right, hopefully we saw how to use the second derivative test to find an absolute minimum in that example, and you had a little practice with that on one of your homework problems, exercise 31. Now it's time to look at an application. All right, so you have a 25-inch by 20-inch piece of tin, and you're going to take this piece of tin, and equal size squares are cut from the corners. And when you take and you cut equal size squares from the corners, you can then fold the flaps up and create a box. It's an open top box. So we're going to determine the size the squares need to be so that the resulting box has a maximum volume. So here's like a quick diagram of what this would look like. So there's the piece of tin, and we're going to cut squares out of each corner. So each square is x by x. So get this in your notes because I'm heading off to the chalkboard to work through it. All right, there were a lot of words here to kind of go over them one more time. you have a 25 inch by 20 inch piece of tin, and it's going to have equal size squares cut from its corners. So I've sketched in those squares that will be cut from the corners, so that when the flaps are folded, a box is created. So you're cutting these 4 squares, you're removing it, and you're going to take these flaps and fold them up and create a box. It's an open top box. Determine the size the squares need to be so that this box has a maximum volume. Alright, so you have to remember that volume equals length times width times height. So let me look at, well, I think the height of the box is going to be x, the size of one of those, squares that's cut out. When I take this and I fold this flap up, this dashed line would represent the height, which is going to be x. So we just have to figure out the length and width of this box. Well, let me kind of highlight in this blue chalk right here and right here. One of them's the length, one of them is the height. Well, and then this side, this piece here would be the same as that, and this piece here would be the same as that. Well, let's write down what that would be. We know this side is 25. And then we're going to cut away x and an x. So it's 25 minus x minus x. Well, that's 25 minus 2x. Similarly, this side, well, we know it's 20. So this would be 20 minus x minus x. 20 minus 2x. So I think now I can write down the volume. I can write down the volume of the box as a function of x. X is going to be the size of the cut that's made. So let me write that down. Volume is a function of x. Length times width times height. X times 25 minus 2x times a 20 minus 2x. Now I'm going to write down what the reasonable domain is here. Okay, x is representing a measurement, a cut. How many inches I come in and cut. So x is inches, so it can't be a negative number. I don't even know what that would be to say, hey, go -3 inches. That doesn't make any sense. So x can't be a negative number. X can't be 0 because that would be, if x were 0, we're not making any cuts at all. And so our piece of tin wouldn't be a box, it would just be a flat piece of tin. So I think right now, I know that's the reasonable domain. It's getting a start. It can't be 0, it must be larger than 0. So now what's the largest value that this x could be? Well, I don't think it can be 10, because this side measures 20 inches. So if I said to come this way and cut a 10 inch by 10 inch square, and then come this way and cut a 10 inch by 10 inch square, you'd come 10 inches this way, 10 inches this way, and you'd be cutting. There wouldn't be anything to fold up. So it's going to have to be less than 10. It could be 9.2 inches. That's the open interval. We're trying to optimize this function on that open interval, so we have to use the techniques of this section. So I have a little bit of work to do. I'm going to multiply all this out. And let me just say, when you multiply all that out, you're going to end up with a 4x cubed minus a 90x squared plus a 500x. All right, so we get the derivative. So the derivative is a 12x squared minus a 180x plus 500. And since I know I'm going to have to use the second derivative test, let me go ahead and write down the second derivative. It's 24x minus 180. So we need to know, where does the derivative equal 0? All right, folks. As much as I'd like to say, hey, let's try to factor that, I'm not going to waste our time here. This is not going to factor. So we have to use the quadratic formula. So we use the quadratic formula. Remember the quadratic formula. I'll verbalize the quadratic formula as I'm writing in the numbers. The quadratic formula says x equals the opposite of b. That's b. So the opposite of b plus or minus the square root of b squared minus 4 times a times c, all of that over 2 times a. All right, so if you take a negative 180 and square it and then subtract 4 times 12 times 500, you're going to end up with, under the radical, an 8400. And 8400, see, 8400 is 400 times 21. So that means I can simplify this radical to 20 times the square root of 21. And I can go a step further and do some canceling here and simplify this down to 45 plus or minus 5 square root 21 over 6. Okay, now I need to get a decimal approximation for these two possible answers. 45 plus 5 square root 21 over 6 and 45 minus 5 square root 21 over 6. And when I do that, only one of those will be in the interval 0 to 10. And that one that is in the interval 0 to 10 is the 45 minus 5 square root 21 over 6 as a decimal. I think that's about 3.68. So that is our critical value in that interval where the derivative is 0. So we evaluate the second derivative at 3.68. And what you end up getting, you're going to get a negative number, which tells you you have an absolute max at x is about 3.68. So the question was, determine the size of the squares that need to be cut so that the resulting box has a maximum volume. We have it. That's what the x is. So you need to make cuts of squares that are about 3.68 inches. And you could actually find all three dimensions. We know the height is 3.68 inches. You could put 3.68 in here for x and 3.68 in there for x to get the actual dimensions of the box that would have maximum volume. And you know what? If you do that, I just have enough room right here. This is like bonus information. It's a box, it would be 3.68 inches by 17.64 inches by 12.64 inches. Okay, we weren't asked to give all the dimensions, but I thought, hey, while I'm here, I might as well do it. All right, let's head back to the slides and see what is next.
All right, hopefully we saw that application of making the box with, maximizing the volume wasn't too bad. I'm going to briefly go over like a general strategy for doing an applied optimization problem on an open interval. The first thing I say is, understand the situation. So what does this mean? Well, it means you have to read the question carefully And if it's possible, sketch a picture that represents the situation. So like in that last example, we had a picture there that represented it. Select the variables to represent the quantity to be maximized or minimized, as well as any other unknowns. Then you want to write an equation for the quantity to be maximized or minimized, and determine the interval or the reasonable domain over which the function is to be optimized. If necessary, you might have to eliminate extra variables so that the quantity to be optimized is a function of one variable. Continuing with this strategy, after we do number 1, then we're to step 2 where we perform the mathematics. So if the interval is an open interval or a half open interval, we have to use the techniques of this section to optimize the situation. However, remember, if the interval is closed, we can use the techniques that we learned in section 5.2. And then finally, interpret the result. So, we're becoming really good at interpretations. So let's see what the next example is. Okay, this is an example. Boy, a lot of words. Please write all these words down. Someone has an organic apple farm, and they found that each of the semi-dwarf-sized golden delicious apple trees produce, we'll say, 300 apples per year, when the number of trees per acre is 40 or fewer. Okay, now Uncle Johnny would like to maximize the annual yield per acre by planting more apple trees. Now, it's been discovered that for every tree over 40, the annual yield decreases by 5 apples per tree due to overcrowding. So under that situation, how many trees should be planted on each acre to maximize the annual yield from an acre? So please get this written down. There's a lot going on here. We have to do a lot of analysis, and we're going to head off to the board to do all of that.
All right, folks, we just looked at some general guidelines on how to attack these problems. And then this example had a lot of words. Uncle Johnny's organic apple farm has found that each of its semi-dwarf sized golden delicious apple trees produce 300 apples per year when the number of trees per acre is 40 or fewer. Now, Uncle Johnny would like to maximize the annual yield per acre by planting more apple trees. Okay, it was discovered that for every tree over 40, the annual yield decreases by 5 apples, that's per tree, due to overcrowding. So how many trees should be planted on each acre to maximize the annual yield from an acre? So I have a little work to do here, and I made a table, like a chart over here, to try to figure out what is happening in this problem. So we know that if we have 40 trees per acre, 40 or fewer, you're going to get 300 apples per year. So let me kind of put that in here. If you have 40 trees, the yield per tree, you get 300 apples per tree. So the total yield would be, I'd multiply those together. So let me just write that down. It would be 40 times 300. So that's like 12,000. That's a lot of apples. Okay, now we know for every tree over 40, the annual yield decreases by 5 apples. That's 5 apples per tree due to overcrowding. All right, so every tree over 40. So let's see what it looks like if we have 41 trees. So if we have 41 trees, we know that the yield per tree is going to go down 5. So this would be a 395. I'm sorry, it would be a 295. A 295. So I'm not going to just write in 295. I'm going to write that a little differently. It's 300. Well, it's 300 minus 5, right? You lose 5. But I'm going to write that like this. 5 times 41 minus 40. 41 minus 40 is 1. 5 times 1 is 5. 300 minus 5 is 295. So, let me continue on. See if I can detect a pattern. If we had 42 trees, per acre, well, we'd lose another 5 apples per tree. So this should be 290. You should have 290. So let me write that down. This is 300 minus 5 times 42 minus 40. I should probably write this. We know this is 12,000. This here, if you do this multiplication, if you do 41 times 295, you're going to get 12,095. Here, if you do 42 times 290, because this ends up being 290, you get 12,180. So look, we're getting more apples, aren't we? Let's do one more row of this chart I'm making with an actual number. If we go to 43 trees per acre, we're going to lose another 5 apples per tree, so this better be 285. I'm trying to detect a pattern. So trying to detect the pattern, I would write that as 300 minus 5 times 43 minus 40. Yep, that would be 285. So 43 times 285, well, that would give us 12,255 as the total yield. I could keep going and hopefully guess the correct answer, but I'm ready to generalize. I don't know how many trees to plant on each acre, and that's the question here. How many trees should be planted on each acre? So let me call the number of trees planted on each acre X. So X is the number of trees. Let's follow the pattern here. Looks like we would have 300 minus 5 times, well, notice, so I think that should be an X. And then the actual total yield will be this times this. So X times 300 minus 5 times the quantity X minus 40. I think we now have a function for our total yield. Let's let f of x represent the total yield. So let's call this function f of x. So we have f of x equals x times 300 minus 5 times x minus 40. Alright, so I got to clean this up just a little bit. Inside the brackets, I would distribute the negative 5, combine like terms, then distribute the x, and I end up getting negative 5x squared plus 500x. Okay, now what is the interval? Well, I'm going to say we better have at least 40 trees. I mean, if we go with 38 trees, 40 or 38 times 300 is going to be less than 40 times 300. So we're going to need at least 40 apple trees. I mean, heck, I think we're going to need even more than that, as the table tells us. But what's the most number of trees we could put on an acre? There has to be an upper bound. I don't think I can get 50 million trees onto 1 acre. Well, if I quickly look at this function and I say to myself, well, when would this function that represents total yield, when would it be 0? Well, I could solve that for 0. I could set this equal to 0 and solve, and I'd end up with 100. Now I'm putting a parenthesis around that because if it were 100, my yield is going to be 0. So it has to be less than 100. So I have a half open interval. I need to use the techniques of this section to find the maximum and how many trees should be planted to maximize the annual yield for an acre. So we better get the derivative. So here the derivative is negative 10x plus 500. While I'm here, I might as well write down what the second derivative is. It's just negative 10. That was pretty easy. Set the derivative equal to 0. And we end up with x equals 50. It's the only critical value that's equal to where the derivative is 0. I evaluate the second derivative at 50. And heck, I get negative 10, which is a negative number. It's a negative number. That means we have an absolute max at x equals 50. And again, what did x represent? The number of trees planted per acre. So the answer to the question was, how many trees should be planted on each acre to maximize the annual yield from an acre? 50. So you're going to plant 50 of these semi-dwarf sized golden delicious apple trees. And that's it. So now you've seen enough that you can attempt the exercises in section 5.4. They may take a little bit of time. Take your time with them. But now head off and do the exercises in section 5.4. Thanks for watching.